Welcome to The Explainer. Today, we're diving into one of the most incredible logistical challenges on the entire planet, managing the electricity that powers literally everything we do. It's a supply chain, sure, but it's not like anything you've ever seen before.
All right, let's start with something we all get, a normal supply chain. You know how it works, right? You take some raw materials, you make a product, stick it in a warehouse, ship it out, and boom, it's in a customer's hands. It's a physical thing on a physical journey. Pretty straightforward.
But what if the rules were completely different? Imagine trying to manage a product that's totally invisible. You can't put it in a box, you can't stack it on a shelf, and get this, the very second you create it, it has to be delivered and used. No inventory, no delays, nothing.
And that, my friends, brings us to electricity. It's basically an impossible product. It shatters every single rule of a traditional supply chain, and because of that, we had to invent a completely new kind of system just to handle it.
So here's the absolute heart of the challenge. Managing electricity is a real-time, high-wire balancing act. You can't just make a bunch of it and save it for later, like you would with, iPhones. The instant you flip on a light, a power plant somewhere has to spin up and generate that exact amount of energy to meet your demand. Supply and demand have to be perfectly matched every single second.
So how on earth do you manage something like that? Well, you build a very special piece of infrastructure to handle this impossible product. We call it the power grid. Think of it as the circulatory system for our entire modern world, designed for one thing, that crazy real-time balancing act. And the grid itself? It's changing. Big time. We started with the traditional model you see on the left. You know, a few huge power plants pushing electricity out in one direction. But now, we're living in the world on the right. It's a complex, distributed web. Power is flowing in all directions, from big plants, from wind farms, and even from solar panels on our own rooftops. It's gone from a simple one-way street to a chaotic, multi-lane superhighway, which, as you can imagine, way harder to manage.
But look, no matter how complicated the grid gets, the journey of that little electron still follows 4 basic steps. First, you've got generation. Then that power has to travel, sometimes hundreds of miles, through these massive transmission lines. From there, the voltage gets stepped down for local distribution. And finally, it all ends with consumption, that magic moment you flip a switch and your light turns on.
So let's just pause here for a second. If you can't see it, you can't count it, you can't hold it in your hand, how do you possibly manage it? How do you even know if the system is healthy or if something is going seriously wrong? Well, the answer is data. Grid operators live and die by this rule you see on the screen. They use things called key performance indicators, KPIs, to act as their eyes and ears, constantly measuring the health and the efficiency of this invisible flow.
Now, of all the data they track, there is one KPI that is absolutely critical for any utility. It's called system loss. And the idea is actually pretty simple, but the consequences are huge. It's the gap between all the power they generate and the power that they actually get paid for. And for some systems, this number can be just staggering, as high as 12%. I mean, think about that. Imagine you're a car company and you make 100 cars, but by the time they get to the dealership, 12 of them have just vanished. For big utility, that 12% can mean hundreds of millions of dollars in lost revenue every single year. Which of course leads to the million-dollar or more like billion-dollar question that keeps every utility manager on the planet up at night. If you're not storing the power and you're not billing for it, where in the world did it go? Okay, so obviously the power isn't just vanishing into thin air, it's being lost. And the real job of managing this impossible supply chain is a constant, non-stop battle to find and plug the leaks in the system. And these leaks, they really fall into 2 big buckets. On one side, you have technical loss. This is just pure physics. It's the physics problem. As electricity zips through wires, some of that energy just naturally escapes as heat. You can't stop it. On the other side, you have commercial loss. This is the people problem. This isn't about physics. It's about power that gets used but never paid for because of theft, messed up meters, or just simple billing mistakes.
And this whole idea of energy loss, it's totally fundamental. I mean, anytime you convert energy from one form to another, some of it gets wasted, usually as heat. So the goal for a power grid isn't to get technical loss to zero, because you can't. The goal is to fight for every tiny fraction of a percent at every single step of that journey.
So how do you fight these losses? Well, utilities have a pretty clear 4-step playbook. First, you have to diagnose. You got to figure out what kind of leak you have and where it's happening. Then, once you know that, you can harden the grid with better equipment to fight that physics problem.
Next up, you protect revenue. That means tackling the people problem, the theft, and the errors. And finally, you digitize everything you can to automate the whole process and take human error out of the equation.
And this gives you a real sense of the tools in their toolbox. For a technical fix, it could be as simple as swapping out old wires for new, more efficient ones. To fight commercial loss, they might install prepaid meters or even conduct raids to stop power theft. And on the digital side, something as simple as an automated billing system can wipe out an entire category of human mistakes.
So the main thing to take away from all this is that the job is never, ever done. Managing the power grid is just this continuous loop of measuring, diagnosing, and fixing. It's a relentless, 24/7 effort to maintain that incredibly fragile second-by-second balance between what's made and what's used. And that really leaves us with a final, pretty fascinating question for the future. As more and more of us put solar panels on our roofs, our own homes are becoming tiny little power plants. That grid is no longer a one-way street. It's that chaotic superhighway we talked about. So the real question is, in this new world, how is this already impossible management challenge going to evolve?